Everyone to today's version of the Inverse Problem Seminar. We are very happy today to have Richard from University of Cambridge to give a talk. He has done a lot of important work in mathematical statistics, in particular interdimensional statistical models and Bayesian inference. And he also got a Prose Award for a book on mathematical foundation on infinite dimensional statistical models. So yeah, be happy to have him here live today. So thank you, Richard, for coming and giving a talk in our seminar.
All right. Thanks so much for the introduction and the invitation. And it's a great sort of nostalgia to give a talk on Zoom, which I haven't done for a while. So, but it's great to have this community, and I think it shows how useful Zoom is. And since it's already late in the day for me, I hope I won't be too tired, but I'll do my best. So this talk is about some work I've been doing recently on sort of making inference on parameters and the state of a sort of system that arises in a parabolic time evolution equations, where there is somehow an inverse problem, a nonlinear inverse problem lurking in the background, but also this is actually one of the traditional areas of where people have used Bayesian statistical inference in partial differential equation models even before the boom on Bayesian inverse problems came about. And actually, somehow, now that we've made some progress on this theory of Bayesian inverse problems, it's also interesting to reconnect a bit to the old problems where people have been using Bayesian statistics in PDE models already for a long time. And so I'll try to review this a little bit. Because this really comes from applications originally. The Bayesian methods in these settings have been used by engineers and scientists and not primarily by mathematicians, where you have some sort of time evolution phenomenon that typically, to make what I will speak about non-trivial, has some nonlinear aspect, which is basically the state of some vector field or some system at some time t and some space variable x. And then you sort of start this at some initial condition and you run this through time, and maybe the state space is some d-dimensional domain that I will call omega. And the dynamics is somehow nonlinear, and it is described for the purpose of this talk by a partial differential equation. So the theory that I will develop has three examples in mind, which really do come from applications. The first is used in atmospherical modeling and weather forecasting on oceanology, which is just the Navier-Stokes equations. Then you also, in chemical applications, you often have reaction diffusion phenomena. And there's also interacting particle systems that I studied as a nonlinear PDE recently, quite frequently, the Minkine-Vlasov equations. And they're somehow all of a general form where you have a time derivative and you have a Laplacian that is fixed for the moment, so we don't put something unknown into the Laplacian. And then you have some sort of nonlinear functional of the solution of the PDU that describes, for instance, in Navier-Stokes, maybe the gravitational effects, or in Minkine-Vlasov, it describes the interaction effects, and in reaction diffusion models, it sort of describes how sensitive your substance is created or destroyed at a point in time, independence of the state of the system. Yeah, so these are kind of well-studied nonlinear parabolic partial differential equations, and somehow they pop up in applications frequently. Of course, somehow, if you go back to the 19th century, you could think of the typical determinism that people who write down differential equations like, where you just basically say that once you've written down your equation, you know everything. You know? So Laplace made this nice thought experiment where he said that an intellect which at a certain moment would know all forces that set nature in motion, sort of that has basically worked out sort of your PDE, would embrace in a single formula the movements of the greatest bodies of the universe and those of the tiniest atoms. For such an intellect, nothing would be uncertain, and the future, just like the past, could be present before its eyes. So this is a typical vision of mathematicians and physicists of the early 19th century, where they thought that ultimately, at the end of science, we will know everything forwards and backwards. And of course, for a statistician, this is a very nice hubris to challenge, because really there's always uncertainty when you have real data. The first thing that in these scientific applications is typically unknown is just the initial condition of your system, because you're sort of making measurements already forward in time and you don't really know where your system has started. And also there's the ubiquitous discretization error, where you sort of make measurements of the state of your system at discrete points in time and space. And then you get these response variables, and the data you collect are actually just these measurements at the design points xi and ti. And for the purposes of this talk, just to make life a bit easier, we'll assume that somehow this discretization gives equal importance to both space and time variables. So we believe that we measure space and time sort of basically by an independent, identically distributed random sample. This is not always realistic, but it allows us to develop some of the theory more easily. In engineering applications, they also often believe that the PDE model is wrong, and then they, maybe not wrong, but only approximately correct, and they don't often write a sort of model error term into this equation as well. This is when you speak of filtering problems in engineering and sciences, usually part of the story. I will not consider an additional stochastic model error term here, but I will just view this as a regression model where you basically see the solution of your phenomenon evolving in space and time with additive Gaussian noise. So the error distribution here is assumed to be normal in some either in the reals or in some vector space when you have a vector field data. And so what people actually did, and this is actually where a lot of this Bayesian inverse problem stuff comes originally from this literature where people used Gaussian process priors and Bayesian inference already in the 90s, long before Andrew Stewart and even the Finnish school started to introduce this in inverse problems, is you have this PDE model. There's actually no inverse problem. You just want to infer the state of your system and predict it forward. But because it is rather difficult to choose a good prior on a set of solutions of, say, Navier-Stokes equations, what you do is you put your prior on the initial condition. So you model the initial condition by, say, a Gaussian random field, and then you feed this forward through your dynamics to create sort of a prior guess in the trajectory of all possible trajectories, in the space of all possible trajectories. Yeah? So if you think of this, the prior model is just a device to draw some sort of initial guess of the random function that represents the initial condition. And then because you have well specified your PDE model, this gives you also a prior on the solutions of your nonlinear system, okay? So in some sense, actually what you're trying to model is the space of trajectories in time, but because you don't know how to do this easily, you put a Gaussian process prior on the initial condition, and then you sort of feed this into your dynamics. If anyone has questions, please do interrupt me anytime. Yeah? So this is, I mean, the references I've given you are sort of recent books on data assimilation, but these ideas were actually already pursued in the early 90s, where people would not usually do posterior sampling. They would do some optimization method, but the setup really comes from there. And it comes from engineering and sciences. And if you go to these references, you'll see some very old references that predate all this Bayesian inverse problem stuff. Okay, but it is interesting to see that somehow inbuilt in this approach, there is an inverse problem, because when you compute the posterior distribution from the data by the usual formalism from your regression model, you will reweight sort of the likelihood term, which in this Gaussian regression model is just this sort of exponentiated negative least squares potential. And then you reweight it by sort of the covariance norm of your prior, which is some Hilbert space norm, like a Sobolev norm or something like that squared. Okay, so what that means is that your initial update of how you're going to predict your system doesn't happen in the trajectory in time. It actually, the initial update happens at the initial condition. And this, we will soon see, is actually, of course, an inverse problem. So your success in even predicting forward will depend on how well you do in solving your inverse problem. So if you work on inverse problems, this is sort of something that appears on the way in the analysis. It is not actually set up as an inverse problem because the task is rather prediction. But it is, if you set it up this way, there's an inverse problem sitting in there. And you, of course, once you have your posterior on the initial conditions, which is a hard problem to solve, you can then feed it back into your dynamics and compute sort of the updated system under your PDE forward model, where your initial condition now is drawn from the posterior. Okay, so it's very clear that if your U theta to U theta map is a solution map of a nonlinear PDE, where theta is the initial condition, that the posterior will already be not, even if your prior is a nice Gaussian distribution, the posterior will not be Gaussian any longer because you have this nonlinearity sitting in here. And then the posterior and the trajectories will be even less Gaussian, sort of doubly nonlinear, because you feed the nonlinear evolution dynamics into the posterior as well. So it is very clear that both these objects, the posterior on theta and the posterior on the trajectories, are very complex objects that are random probability measures in an infinite dimensional space. And whether you can say something about them theoretically, basically until maybe a few years ago, there was nothing. But in applications, these have been widely studied, and well, not studied, but people have tried to sample from such models, particularly in the Navier-Stokes model. This is sort of very closely related to filtering problems in atmospherical science. One method that people would use in a linear dynamics is the Kalman filter. And this has been sort of adapted to nonlinear situations. And even though there's no theory that gives guarantees for this ensemble Kalman filter, this is very successful in practice. And if you want a recent reference on this, maybe from a more theoretical point of view, you could check out this preprint, which is on the archive. But sort of there are lots of methods that try to compute, in particularly the distribution of the system at the last observed time, Tn, if you want, which is sort of the maximal order statistic of the time measurements. And they have in particular an appetite to do this sequentially. So when they collect more time data, that they don't have to recompute the whole trajectory, but they do it sort of step by step. So that's why these are sometimes called filtering distributions. But you could also do other methods. You could just do your Markov chain Monte Carlo method for the inverse problem on theta. So you pick up a Markov chain that has, as in like the posterior distribution on the initial condition as invariant measure, and then you can do your favorite like gradient type Langevin algorithm or PCN or whatever, and you can sample from theta, and then again use your forward model, and so you can somehow create approximated samples from these potential trajectories in the posterior without ever having to back integrate your nonlinear PDE, but you only need to evaluate the forward map. Yeah? So in some sense that this is attractive in practice should be clear, but it is also something that it's not so clear whether this actually works. Yeah? So the types of nonlinearities that you can look at in practice, and I obviously will want to present some theory about these posterior distributions, that one could look at is sort of, as I said, these nonlinear equations are of the form time derivative is Laplacian, and then you have some nonlinear terms. So in Navier-Stokes, you would have this usual sort of bilinear form involving sort of the divergence of your vector field. Then the model that I will mostly study here today is this reaction diffusion equation, where you have a nonlinear function acting on you by pointwise composition. And let's say these are not vector fields, but just scalar functions, then you would have a function f of a real variable. And in these interacting particle systems, you actually have a more complicated sort of bilinear term that involves sort of convolution with an interaction potential W. Okay, so these are all sort of examples of such nonlinear settings. There are, of course, many nonlinear PDEs that we could write down that have a time evolution aspect. So the theory will potentially look different. In these examples, we have something that makes them dissipative, which means that somehow the complexity of candidate solutions becomes less as you move forward in time. Sort of in the extreme case that you would measure until the end of time, you would have often a finite dimensional attractor in these models, which means that somehow eventually, if you run this for a long time, you would get a very sort of rather low dimensional sort of set of possible solutions, which however also means that a lot of the statistical information is lost because a complex infinite dimensional initial condition becomes sort of compressed and dissipates into something low dimensional. So actually I believe for a statistical point of view, the most important regime is when you make measurements in a fixed finite time horizon that starts measuring basically now when the data starts to be collected. So I don't think it is so interesting in these models to look at the like long time horizon dynamics. And so what I really want to talk about is sort of what statistical properties posterior measures in such models have, both for the inverse problem on the initial conditions theta, and then also for the entire system U theta that we get by sort of updating in the space of trajectories. And the asymptotics that we do as statisticians here is, as I said, is not letting t go to infinity, which is maybe someone from dynamical systems will do that, but we want to say what happens if I collect informative data, so I have like a large sample size n going to infinity, and then we make probabilistic statements under the distribution or law of the observation Zn, which of course on average will tell me something about the signal, particularly if I have lots of data. Yeah? So somehow when we analyze such posterior algorithms to solve inverse problems, we take this probabilistic perspective or frequentist perspective where you have this data, but we do not adopt the Bayesian formalism in our analysis. We actually have a hypothetical ground truth condition, initial conditions theta naught. So somehow this is still a scientifically objective way to give guarantees for algorithms. The Bayes method is only used to conceive the algorithm, but is not used to give guarantees for it. Okay, and so what I will say is to a certain degree representative of all these three examples, but the results are most worked out for the reaction diffusion equation. But the first result that I will just talk about briefly is just a simple posterior consistency result for the two-dimensional Navier-Stokes equation. So this is important because these are arguably the most is the PDE where most people use these methodologies. So maybe one should try to say something about what happens in this PDE. Obviously, if you do theory, this depends on the existence of well-posed solutions to this PDE. So I can only do this in 2 dimensions at the moment because for Navier-Stokes, this is still open in 3 dimensions. But something that we were able to prove is just sort of a basic sanity check that if you take, you need some conditions, obviously, on this Gaussian process priors. But if you take a correct one, then actually these updated posterior trajectories will concentrate near a Dirac measure at the true trajectory that is generated by the initial condition that sort of made the observations. And also the posterior mean vector, which is what you usually compute by MCMC, will converge to this ground truth. And the rate we get here is, however, only delta n, which is sort of a logarithmic inverse rate in the number of samples we obtain when we sort of have a moderate time horizon in the measurements. Yeah? So what this means is that we can, and this is actually proved by showing that the same logarithmic rate is obtained by solving for the initial condition in the Navier-Stokes system, and then you feed it forward into your dynamics. So there's some consistency, meaning that these posterior measures eventually do sit at the Dirac measure at the right ground truth, but the rate here is not yet overwhelmingly fast. But at the same time, this is a robust result that holds sort of for general initial conditions that just need to be sort of bounded in an H alpha sense. So I have an infinite dimensional statistical model that underlies this problem. And this is based on a logarithmic stability estimate that you can prove for this Navier-Stokes equation inverse problem. So you can basically control the L2 distance between the 2 initial conditions that generate a trajectory in Navier-Stokes by an inverse logarithmic modulus of continuity. And if I allow my initial conditions to be sort of bounded in, say, H1 or H2, then one can also give a lower bound and show that this logarithmic modulus of continuity is necessary. And I should have clarified in this statement here that this is for fixed positive t. Yeah? So if I actually decide to measure only at one point t forward in time, you cannot actually somehow beat this logarithmic ill-postness, at least for the Navier-Stokes problem. Okay, so there seems to be one aspect that says maybe these problems are not good for inference because they're too hard, because somehow all the information is washed out after when I measure at a positive point in time. And the way this is proved is sort of clever, but not very deep. So what you do is you just take the Dirichlet ratio between sort of the H1 norm of the difference of your solutions and the L2 norm, sort of like what you would consider when you do a Poincaré inequality. And then what you do is you need to prove a clever differential inequality in time for this ratio. And of course, once you have the right differential inequality, you just do Grönwald and do it sort of, it's not difficult, but to get the right inequality, you need to use a few clever inequalities for 2-dimensional Navier-Stokes. And my co-author Idris Titi, who is an expert on these things, was certainly helpful in the process. Yeah. So somehow this says that maybe these dynamical systems are too hard and like for statisticians, maybe not so interesting because you only ever going to get logarithmic rates like in the Calderon problem. So maybe we should stop here. And I mean, if people want me to stop, I can certainly stop here, but there's sort of a different take you can take on the problem. And the purpose of this talk really is somehow to convince you that you can get faster than logarithmic rates in these models without restricting to a nice finite dimensional model of super smooth functions, because that would be possible without difficulty if you go to a low dimensional model. But the question is, can we actually get meaningful rates faster than logarithmic in these problems when we when we measure somehow such systems. And so in short, the answer is that if you are able to measure more or less at the beginning of time, so if you don't need to wait a positive amount of time, but you can sort of measure from the Big Bang onwards, the answer is yes, and you can give almost a complete mathematically satisfactory description of what these posterior distributions will do. Now, the mathematical techniques that underlie such results are much more complex than what I mentioned on the previous slide. And so I have so far worked this out for a reaction diffusion model, and the work on Navier-Stokes is in progress. But the reaction diffusion model, you can sort of see maybe most clearly what kind of properties will play a role. So again, we have this sort of parabolic equation, and you have acting function f by composition on the function u. And so if f, for instance, is smooth and compactly supported, it's not easy by a sort of Banach fixed point contraction rate argument that this has unique solutions for any initial condition. So we get a well-posed sort of forward map. And the reason why we study this PD in the first place is not so much the reason that this is the most important applications, but it is because the linearization of this nonlinear operator is sort of a heat semigroup corresponding to a time-dependent Schrödinger operator. And for Schrödinger operators, we can do some things and exploit symmetry and spectral theory that is more difficult for other PDEs. So I will mostly talk about this PD for the rest of the talk. Okay, so let's go into what these people would be doing in practice. You use a Gaussian process prior. What do you really do in practice? So here, because we're we'll look at periodic equations only, so we're on the torus, so we need to somehow get rid of the kernel of the Laplacian. So we just like intersect our initial conditions with those that integrate to 0, and then on this you would take what is normally known a Whittle-Matern Gaussian process prior, which on a torus is nothing else than an infinite dimensional Gaussian distribution whose covariance is some fractional inverse power of the Laplacian. So it has some like smoothness in the spatial variable. We'll generally want the smoothness to be here at least 1 plus d half. And I'm really taking the infinite series prior. So I'm not doing a truncation. You could do a truncation too, but somehow if you do it for the infinite series prior, you're most robust because any kind of discretization of your prior that you might use in applications will be permitted. And there's also this usual rescaling trick that François, Gabriel, and I used already in our first papers, and which no one has been able to avoid so far, where you kind of shrink the variance of your prior in a certain way that maybe depends, like I could maybe say, on the effective dimension of your problem, which has to do with the regularity of your prior gamma and the dimension of the domain. So this is by now sort of well-accepted technique. It's just an adjustment of the covariance of your prior that is needed for the asymptotic theory. Okay, so this is what you put on your initial condition in your nonlinear parabolic equation. And then you get your posterior, which is, as I've said before, not a Gaussian measure any longer. And we can also update the whole system, pi hat. And I will just give you like an informal idea of what the main theorem is now. And for those who are interested in the math, I'll try to talk you a little bit through the proof. But if you don't want to concentrate for so long, then I'll just tell you roughly what you can say about this statement. Yeah. Notice that what the engineers and scientists often try to target in their algorithms is the so-called filtering distribution, which is the law of the push forward of the solution of the PD at time t when the initial condition comes from the posterior at the terminal observed time in your sort of time horizon, which, because I'm IID sampling my times, this is just the largest of the observed times, okay? But actually my result will hold for all positive times and even uniformly so it's not specific for the filtering distributions. And we will basically prove a best possible result, which is sort of a Bernstein-von Mises theorem, which says that actually these trajectorial updates at time t, and I will talk about the initial condition also in a moment, but these pi hat distributions, which are the target of statistical inference, they are very complex non-Gaussian distributions in an infinite dimensional space that involve two nonlinearities, one from the inverse problem and one from the forward solver. But somehow surprisingly, they're still universally approximated by a certain Gaussian random function. So what is this Gaussian random function? It's the law, well, it's centered at the solution of your reaction diffusion system evaluate at the posterior mean. So this is sort of the best guess that the posterior would have. So that's what you expect, that is sort of centered at a good estimator that you would compute in practice. But the important thing are, of course, what are the fluctuations? The fluctuations are the scale root n. And in fact, surprisingly, the approximation will hold in a very strong sort of sense of the supremum norm topology on the underlying functions. I'll get to this later in the rigorous statement. But the crucial thing, what is this random function v? Well, the random function v is a solution to a stochastic PDE, where you take the linearized equation, which is again has a parabolic term, then it has a Laplacian, and then it has a Schrödinger term that is time dependent, which is the derivative of your reaction function f at the ground truth solution that generated your trajectory acting on v. And the complexity of the problem really comes through a rough initial condition, which is sort of a draw from a Gaussian measure that has as covariance the inverse Fisher information operator for this model, whose existence needs to be ensured. And this is, in fact, one of the main steps in the proof. But somehow what you see, that the inverse problem goes only into the initial condition. You need to work hard to get the Bernstein-von Mises theorem for the initial condition, but then you just like linearize the dynamics forward. And so you know that the fluctuations of these filtering distributions, for instance, are somehow very easy objects that are just sort of random functions drawn from a stochastic PDE with, or just a linear PDE with Gaussian initial conditions. Okay, so this is roughly the statement for a scientist or engineer that uses these methods, is that when you try to compute these distributions, they are actually not as complex as you think, at least as n goes to infinity, because they're very close to Gaussian objects. Okay, and I think like this means that in some sense maybe gives some interpretation why filtering problems are empirically so successfully solved by these algorithms, because the target distributions, even though the whole machinery looks very complicated, actually they have a very strong approximation by a Gaussian random function. Okay. There are several subtleties here. So one is you have to work out the initial condition, and the other one is to realize that this approximation, well, this is one probability measure, this is another probability measure. So you need to put a metric on the distance, and I will take the Wasserstein-1 distance for this. But the Wasserstein-1 distance is always relative to a topology you put on the underlying function space on which these probability measures are defined. And this is, in this case, will be the uniform norm on the space of continuous functions in both time and space, as long as the time variable is bounded away from zero. So these are much stronger approximations than anyone has ever obtained in Bernstein-von Mises theorems in infinite dimensions, which usually only hold in negative Sobolev norms. They hold in much stronger norms. And this is also surprising, and I will need to explain a little bit why this happens. Yeah? But that's sort of in a nutshell, a statement that filtering distributions in nonlinear dynamical systems in such settings are actually by far not as complex as maybe some of the engineers and scientists that work with them would maybe claim that they are. Yeah? And of course, this will also have opened the door to try to give convergence guarantees for algorithms that target these distributions. But let's first try to understand this theorem. And again, I should say that the covariance that this process attains is not just some Gaussian covariance, but it is the best possible, the smallest in a minimax sense sort of covariance that any estimator can attain in, say, for instance, providing a confidence interval for the true solution of the dynamical system. So there's some optimality claims for the statistical reconstruction from this algorithm that go along with the theorem. Okay, so and I should say that this is crucially reliant on the fact that we can sample uniformly in time from 0 to t. If I only measure at the positive time, I've already given you the lower bound in the paper with TT, so you will only get logarithmic rates. But when you sample uniformly in t, I mean, like in a way, if I had to convince you that this is not all nonsense, in the linear heat equation case, you have some sort of semigroup e to the minus t of some elliptic operator. And if you integrate this in time, I mean, you know, it's just sort of a formal calculus. You will get the 1 over lambda times identity minus something that is already compactly smoothing. So somehow the forward model, when you integrate it in time, becomes more like an inverse Laplacian. Okay, so we see that somehow, I mean, this of course for linear, this is for linear semigroup. And of course, for me, everything is non-linear. So somehow you can't argue like this at all, but it shows you that in principle, measuring at the beginning of time of an explosion of a semigroup will give you, will make the inverse problem less ill-posed. Okay, so you want to be able to measure the Big Bang, or if you want to translate this into the language of Navier-Stokes, you could say that you want somehow the small viscosity limit where the explosion doesn't go too quickly, and actually somehow you can still see some of the gravitational forces interacting before everything kind of goes to equilibrium. And indeed, you can prove, that's just the first step, that you can get fast convergence rates, that somehow the information distance of your model, which is this integral of the L2 norm in space squared, has a lower bound, not sort of a logarithmic type, but you have a Lipschitz stability estimate where you can put the h-1 norm on the initial condition. Yeah, so this is, and once you have this stability estimate for the global problem, then you can use sort of the arguments that François and Gabriel and I first used in different settings and that have now been written up in a general setting in my lecture notes to fairly quickly show that actually the posterior, when you have data sort of sampling uniformly from the beginning of time, will give you a convergence rate that is actually algebraic in inverse sample size. And as your model gets smoother, you can actually take this exponent a to approach a half, which sort of corresponds to a regular model. So really, I've put this in magenta. The main message, this is already proved for the nonlinear equation, and I will maybe explain. You need to, so the idea is to linearize, then you still have a time-dependent operator, which is a problem, but locally at 0, you can approximate it by a time-independent, sorry, you should say locally time-independent approximation, and then you just have a Schrödinger operator that is sort of at some constant in time interval, and for this you can already do spectral theory and kind of get sort of some semi-group argument like this working, only that you have to express everything in the eigenfunctions of this operator, and then you use stability and the fact that this space has a finite dimension, this operator has a finite dimensional kernel. Yeah, so this is sort of in a short, is the reason why you can get a Lipschitz stability estimate here. And okay, and you get these fast contraction rates, which are a prerequisite for any type of Bernstein-von Mises theorem proof, because you first need to show that the posterior localizes before you can zoom in and say that it starts to look Gaussian. Okay, and this is really, in the language of PDEs, it is what I've said, but in the language of statistics, it means that if you have a semi-group like this, most of the information looks to be at the beginning of time and not later. Okay, so waiting for your system to equilibrate is maybe nice to find an equilibrium, but it will actually wash out most of the statistical information. Now, once you have that, you can go and prove a Bernstein-von Mises theorem for the inverse problem, which is a hard thing because the inverse problem is still ill-posed, so you don't, and it's an infinite dimensional problem, so you don't expect an approximation for the initial condition in very strong topologies. And indeed, following previous work of various co-authors on this topic, what you can show that there is a limiting process and that there is an inverse Fisher information, which I will explain on the next slide. But if you grant that for the moment, and let's just for simplicity assume the initial condition is smooth, so not your statistical model, but the true initial condition is smooth, and your reaction function is, as we said, compactly supported and also smooth, and you use usually maybe finite regularity prior, but somehow smooth enough that the discretization error can be controlled, then the law of the posterior of the initial condition minus the posterior mean at root n rate will converge to a Gaussian, but actually in a very weak topology, only in a negative Sobolev space, some sort of Schwarz-style topology where you test sufficiently many nice functions. And in fact, K even has to be larger than 3D. So you get convergence to something Gaussian, but this is not something you would see in a picture. It looks more like in a very rough sense, there is some limiting process. But it's not one like that you could maybe give a graphical interpretation for the notion of distance between these distributions. And this is actually, well, I mean, it is for an infinite dimensional prior, and it is also for like a hard inverse problem. So formally, the result is new, and also the work is involved is significant, but somehow modulo getting the global contraction rate at a polynomial rate, which I explained in the previous slide, and the inverse Fisher information, which is the key to the whole story, you can draw from existing techniques. And I've mentioned some papers here improving this theorem. Okay, but I should mention that we have already found very basic PD examples, like sort of the standard textbook Darcy PD example, where the Fisher information that you need to invert to make sense of this limit process may not exist. Yeah? So this is work I did with Gabriel a few years ago. So it's not at all clear in PD models that such Fisher information operators always exist. So let's look at what is required to do that and how we can do it here. So for this, I need to review one or two definitions from sort of statistics. So first is sort of the score operator, which is sort of the linearization of your regression map, which in our case is just a forward map. So because the parameter lives on initial conditions and the regression functions live in this parabolic L2 space, you basically need to linearize the flow in space depending on the initial condition. And in fact, for reaction diffusion models, this is sort of well known that you can do the formal engineering calculation and just take the derivative of the reaction function and let it act as a potential. And this gives you actually the linearization of the flow. And somehow the perturbation of the initial condition now becomes the initial condition of this linear PDE. Yeah. So if you linearize your operator in the H direction, then the linearization will act on H as an initial condition. And as H goes to 0, because this is now a linear parabolic PDE, of course, this will be a continuous operator in the appropriate topology. So this is the score operator. This is something that is easy to understand. It's just a time-dependent parabolic solution operator. The difficulty with the Fisher information operator always comes from the adjoint that you need to compute, because the information operator in this statistical language actually needs you to take this score operator and pull it back into the L2 space. So you need to take the formal adjoint coming now from the parabolic L2 space to the standard L2 space. And if you think about what this involves here, this involves integrating in time, but it also involves running this time evolution equation backwards. And because the potential here is time dependent, you don't have reversibility here. So it's not so clear how this I star will act. Yeah? So this is sort of one of the main challenges in showing that this information operator has an inverse. But if you want to have any type of Bernstein-von Mises equation, theorem, you need to solve the information equation. And if you want to have it in a function space, you actually need to solve this equation for any psi in HK, maybe intersected with the functions that integrate to 0, so you can kick out the constants. But so you need to take this operator and write down this equation and solve it, find a solution psi tilde. This has turned out to be a hard problem in PDE problems. So for Schrödinger equation, this was something I did like a few years ago. And then with François and Gabriel, we managed to do this for non-abelian X-ray transforms. For other PDEs, this is still largely open, except for Darcy's problem, where we gave some counterexamples. And so the question is, can we do this for this particular operator that comes from the linear parabolic PDE? If you can do it, then the limiting process in the Bernstein-von Mises approximation that describes the best possible fluctuations of the posterior has this covariance operator, which is sort of the inverse, which has, you have to work out on which domain you can write this inverse when you study its surjectivity. And sort of the main result maybe of an analytical kind in this setting is that this actually exists for reaction diffusion equations and has an inverse. Yeah? So this operator is basically something like the inverse Laplacian. So if you pre-multiply it by the Laplacian, and I should have written H eta 0 here, where this is where you intersect with the constants. Apologies for this. Then this is actually a continuous homeomorphism. So you kind of map an H eta space into and onto itself for eta large enough, but then also you can of course take the intersection of eta and you get this on the sort of smooth functions on the torus. And the way this is proved entails in particular one statement is that this operator is a compact perturbation of the identity and also Fredholm. So this kind of argument has been used by François and Gabriel and myself earlier, but it appears in a very different form. In particular, it comes in very handy because we have this time-dependent potential, which means that we can't run the parabolic equation backwards, which is sort of the heartbeat in inverting this. But we can sort of approximate at least near 0 by just a constant in time operator. And it turns out because you're not perturbing the second order differential operator, but only the potential, this is already a compact perturbation itself. It doesn't even have to be small. It's just you could take anything, and so that means you just need to prove injectivity if you want to prove surjectivity, because this is a Fredholm operator. And once you have this kind of constant in time approximation, then you have again a Schrödinger operator, which is self-adjoint, so it is reversible, and you can do spectral theory and make everything work and go back to prove injectivity. Yeah? So somehow, if you linearize Navier-Stokes, for instance, this will not give you something reversible, and this is a harder problem. But for these reaction diffusion problems, you can prove this in this way. And what we see from this is also that the Gaussian approximation for the initial condition will not hold in any strong sense, because the measure you get from this covariance is not defined as a proper Gaussian random function. It is only a proper Gaussian measure in HA for negative exponents. So this is a Gaussian process, but not a Gaussian random function. So at the initial condition, your posterior fluctuations are still very rough. and they're not something that would give you a pointwise interpretation of sort of a confidence band around sort of the function you're trying to infer. But this is necessary because this process is what it is, and it just doesn't live in, say, for instance, L2. Yeah, and since you're converging towards it in weak convergence of probability measures, this can only happen if the limit exists as a tight measure. So there's no hope you're going to have an approximation of the posterior in any stronger sense in this inverse problem. But then, of course, you feed this initial condition back into the nonlinear dynamics, and that should be a smoothing map. No, I mean, so in principle, you're solving a nonlinear parabolic PDE. So you would expect that that somehow, even though your initial condition is reconstructed only in very low frequencies and like only the negative Sobolev pairs, when you feed it back into the dynamics, you should gain again. And the nice thing is one can actually make this rigorous in the nonlinear setting. The way this is proved is to linearize again, because we already know that the posterior contracts. So I can basically say that my posterior fluctuation around the posterior mean sort of forward solved PDE at time t is basically the linearization acting on sort of the misspecified initial condition. And then I get some approximation error that I can control because of me already having proved posterior contraction. And now you need to ask yourself, does the linearized equation really smooth? Of course, there could be a kernel. No? So when the Laplacian minus the reaction term has a kernel, the dynamics don't do anything. They just stay stuck. So in this case, you would not be smoothing. And this idea that parabolic regularity helps you would be wrong, because there would be an eigenspace of your operator where you actually don't smooth. You just like stay constant. But the kernel of this Schrödinger operator under this hypothesis is finite dimensional. So that means that the part of the spectrum where nothing happens in the linearized dynamics somehow it doesn't affect more than a finite dimensional part. And this means that this somehow finite dimensional statistical model where the root n rate still survives. And so you can actually really get this done and show that if you go on the space of probability measures in trajectory space being bounded away in time from some positive t mean, which you need for the parabolic regularity estimate to come into play, then you can actually reconstruct the posterior fluctuations in the strong supremum norm sense by the solution of the stochastic PDE. And even though the initial condition is only living in a rough space, the solutions at positive times of this equation already are smooth and live in like the space of continuous functions. So in this case, you can actually really say that the random functions that the posterior will sample from are pointwise close to the true function and also the posterior mean draw, and the error band around it comes from a sort of maximum of a Gaussian random function, and means sort of this is sort of the best of all worlds. And usually in an infinite dimensional model, this is never true. So you can prove that such approximations in a standard regression model are impossible. But in this inverse problem, initially they're also not possible. They only work in this negative Sobolev space. But then, because you're looking at a very smooth parabolic regularity functional of the initial condition, actually you get a very nice result for instance, the actual filtering distributions. And so if you're a statistician, this makes you happy, because you even though you have an infinite dimensional model, you get sort of the usual root n rate of the central limit theorem, and you can even reconstruct the function in a very strong sense. So much of the criticism that we usually get for proving two weak theorems doesn't apply here. So in some sense, these nonlinear parabolic equations are really made for this application of putting an initial condition prior, because the inference for the updates in time are actually much better. And it's somehow, in some sense, for someone from inverse problems, you could say these are not hard problems, even though it might not be easy to understand why they're not hard. And maybe just the last thing, some conclusion and outlook. So even though this proof with the Schrödinger operators will not work for Navier-Stokes, because the linearization of Navier-Stokes is not symmetric, there's still hope to get around it by other techniques, and we're working on this at the moment. Obviously, once you have these approximations, you might want to give some concrete algorithmic guarantees for ensemble Kalman filter or other methods that actually people use to sample from these posteriors. And I think the work we've done will be a starting point for such guarantees, but we're not there yet. You can think of measuring at the beginning of time as something that you could, like as I first said before, think of a small viscosity limit in Navier-Stokes. So somehow when you replace the Laplacian by a small constant time the Laplacian and investigate nu go to zero, then this horizon where you actually have observation, where you have informative data will expand. And so it becomes less of an asymptotic result. And again, if you cannot measure at the origin, these logarithmic lower bounds for Navier-Stokes show that there is no Bernstein-von Mises theorem. And so the conclusion that I've presented here is reliant on you being able to commit yourself to measure from the beginning in time. And for McKean-Vlasov models, I don't quite know how to extend this because this Fredholm argument doesn't work when the nonlinear term also acts on the second order part, when it sort of interacts with the Laplacian. So here I don't really know whether this story is the same, but I will probably end here. Thanks for your attention. And here, so the main paper I talked about is in bold. The Navier-Stokes results are in this paper here. And if you want to read up on the general sort of machinery that we use, you can use these lecture notes, which are also linked on my website. So thank you.
Great. Thanks so much for a great talk. So if somebody have questions, please unmute yourself and ask questions.
I do have one.
Yeah.
Yeah, well, I mean, getting a full BBM theorem is great. I mean, but I think I missed a little bit the actual key point for being able to do that. So this is the fact that you're dealing with, once you linearize, you have something parabolic. Like, let's say you try to do the same thing for a wave equation. I mean, would you run into some sort of serious trouble if you try to prove the full BBM?
Yes.
And we don't know what to do in that case.
Yeah, I mean, so I think, like, philosophically, I mean, like, in some sense, the intuitive answer without doing all the math is just this here, no? So it tells you when you measure average in time, then here like the Laplacian dominates everything at the beginning. So the explosion of the Laplacian sort of at zero before things get smoothed out contains all the information. And the information operator in these parabolic models is basically the inverse, is a compact perturbation of the inverse Laplacian, which is this theorem. And I think this will be wrong.
But do you have that property for the Navier-Stokes equation?
For the Navier-Stokes equations, this should also be correct. I mean, it's not written yet, but I do. It just has to do with the equations of this form. This is on the first slide. Sorry. So basically, if you have an equation like that, and let's suppose f is at most acting on the first derivative of u or on the zero order. Yeah. Then the Laplacian dominates the information operator at the beginning of time. And so somehow all the nonlinearity sits in the lower frequencies and becomes a compact perturbation of what happens of the explosion of the semigroup. And for equations like this, I think the information operator will always be invertible and will be basically a compact perturbation of what I wrote. If you don't have a Laplacian here, or you have some higher time derivatives, or the f interacts with the Laplacian, like in McKean-Vlasov models, then I don't think that the story I'm telling is as simple. I'm not saying it's simple, but it's not as it is.
Great, thank you. Yeah.
And Richard, I have a question. Could you go back to that magic identity that you showed? Yeah.
Which one?
The integral of.
I mean, this is
maybe
not even
this one.
Even honors calculus. This is just integrating the exponential.
Yes. So you're saying this corresponds to what situation? Then you're averaging in time your measurement.
So if you have a standard heat equation, then you're with time-independent coefficients and everything is reversible, then the solution of the heat equation is e to the minus t, the generator, linear now, no? And if you integrate this in time, you could just get the inverse generator. I mean, like anyone who works on Markov processes knows this by heart. And so basically, this is the intuition that when you measure at the beginning of time a heat semigroup, you will get the information, like basically the inverse generator. And like if that is not a severely ill post-inverse problem any longer, because for most of these equations, this is just the inverse Laplacian.
But my question is the dt corresponding to you choosing to sample uniformly, or can you change that measure and obtain different identities and different powers of the Laplacian at zero?
Sure. I mean, so yeah, I mean, if you have some reason to be able to sample, I mean, if you could design an experiment in these models, you would try to sample as closely as you can at the beginning of time and throw away the data that comes later. And by virtue of the theorem I proved, this is not just an intuition, but the Fisher information operator is, when you decompose it, is the inverse Laplacian. Then you pick up things later in time, but these are already compact operators compared to what happens at the beginning. So somehow from the Fisher information, if you want to give the best possible reconstruction of your function, you should basically throw away everything that happens after fixed amount of time. And this, of course, if you cannot really design your experiment like that, but it means, for instance, in Navier-Stokes, that the small viscosity limit will be more informative than when you have a very quick explosion of the semigroup, because most of the data in the uniform sampling scheme will then lie in the first order statistics. If you can choose a different measure in time, you would try to make it almost a Dirac measure near zero, and this would gain more information. I agree with that. I mean, I don't think this can be easily transferred into X-ray or wave equation problems because you don't have this diffusive regime. And so I don't think that the story translates to sort of other nonlinear inverse problems. It really has to do with the presence of the Laplacian that governs the explosion, and the fact that as I said before, that the nonlinearity does not interact with the Laplacian.
And another quick question is just a reminder. So are you going from log type rates to polynomial rates is good for computational purposes, right?
I mean, like any type of theorem that says that the posterior has a shape, like Gaussian or log concave, these theorems are all highly dependent on you getting this contraction rate with the inverse algebraic rate in the first place, because this is a nonlinear problem. You need to linearize, and if you only have a logarithmic rate, the higher order terms, the second order term is just not small enough. So when you have a logarithmic rate, none of these theorems about the statistical properties of posterior distributions are true, other than that you converge to the Dirac measure at the logarithmic rate, but this is not useful to justify statistical inference methods. So if you have a logarithmic rate, none of these stories can be told.
Thanks.
Any other questions for this, Richard? I was wondering a little bit this fact that you shrink the variance of the priors. Sort of, it depends on the smoothness. So what's sort of the intuition, in some sense, for this shrinking?
Yeah, I don't think I've ever given a talk about this without getting this question.
Okay.
And I have no, it's a valid question, and I have to say the question remains the same. My answer is usually changes, but so. Maybe I give you two answers. One is a mathematician's answer and one is a statistician's answer. The mathematician's answer is that this is maybe one of the hardest open problems in my area to remove this the necessity of this shrinkage factor in the proofs. I simply have no clue how to do it. There are many other priors that would be of interest, particularly those that adapt to the unknown gamma, because of course in practice you don't really know what gamma is, and so somehow if you wanted to randomize gamma, which is the typical thing that a statistician would do, I just don't know how to do it. And as a mathematician, I've told all the top mathematical statisticians in my field that if they solve this problem, they probably get, like, maybe at the beginning it was a beer, now it's maybe like a bottle of Dom Perignon or something. So I mean, if someone can figure this out, I just don't know. I was lucky enough that I came up with this in the first place, because otherwise we couldn't do any Gaussian process prior. So as a mathematician, I just don't know. And it's a part that is in the proof is crucial to provide posterior regularization. Now, as a statistician, I can tell you, it's a tuning parameter, and it's common in statistics to choose a tuning parameter in a way that depends on the number of samples, because it is the signal to noise ratio which your problem has should or can affect the best statistical algorithm. No? So N is the number of samples, gamma measures how smooth your signal is. So basically, if you have a smoother signal, you can compress it on a lower dimensional subspace by approximating it. So there's a trade-off between the dimension of the space you need to fit to reconstruct the signal and the number of samples N. And it's very common in statistics that the best method needs a tuning parameter that depends on this, what we call effective dimension or signal to noise ratio. So if you talk to a non-Bayesian statistician, there's no issue with this, because almost every method, like the lasso, which is the most important statistical algorithm that came about in the last 30 years, and every paper has, like, I don't know, the big papers have 10,000 of citations. Like, it also has an independent tuning parameter, and no one has ever asked them why it depends on N and smashed them. No, so, but somehow if you're Bayesian, you think that everything has to be decided almost in Laplacian determinism by the prior and the updating step, and you're not allowed to make the prior depend on N. And my answer is that in high dimensions, this seems to be not always true in nonlinear problems, but I cannot give you a conjecture of whether I believe that this rescaling is necessary or not. I wish I wish it wouldn't be, but I just really don't know. But it is common in statistics to have such constructions, so it's not that we just cooked this up here for the first time.
Okay, thanks. So perhaps also you alluded to it, but if you have uncertainty in the dynamics, sort of the Laplacian, for instance, would something similar, you think something similar could be perceived?
So you mean that like we have a coefficient in front of the Laplacian that we don't know?
Yeah, right.
Like something like this.
Yeah.
Yeah, so this is this has to do also with McKean-Razov, where the nonlinear term interacts with the Laplacian term. This, I mean, also related to Gabriel's question, I think this theorem is only true when the nonlinear term, or I mean, actually, it has nothing to do with the nonlinear term. It has to do with when you linearize that there is an interaction of the unknown parameter with the second order part of the Laplacian. So if I have a because of course this perturbation here that depends on the parameter, and so if this would be on the second order, so if this would interact with the Laplacian, then this theorem I think is not true any longer. And so if you have an unknown aspect on the second order term, this inversion of the Fisher information argument will not at least work in the way it's given here. And my short answer is that I don't know, and the long answer is that I would be doubtful that you might run into some counterexamples like we did in this paper with Gabriel. But this is all completely uncharted territory. So I mean, I was happy to get anything going. But of course, Navier-Stokes and reaction diffusion equations are meaningful nonlinear dynamical systems that people really use in applications. So I think it is sort of sensible, even though it may be simplistic, to invert the information operator in this. I mean, I don't think it's simplistic, but compared to other PDEs, it is simpler. But it is still a valid piece of mathematics to determine that this works on this level. If you have unknown components on the second order term, it will be more difficult.
Great, thanks.
Yeah, thanks for the great questions.
Any other questions? Okay, well, let's thank the speaker again for an excellent talks. Thanks so much.
Thank you. I'll still like